Have you ever wondered how oxygen gets from the air into our blood? Do you know how carbon dioxide gets out of our blood and enters our lungs? While ventilation ensures that air gets into and out of our lungs, it alone does not get oxygen into and carbon dioxide out of our blood. To answer our opening question, we need to look at how gas is exchanged in our lungs. In this context, gas exchange simply refers to the movement of oxygen into the blood and carbon dioxide out of the blood. Oxygen and carbon dioxide move across the respiratory membrane, which includes the alveolus and pulmonary capillary. As you can see from the image on the screen, oxygen moves out of the alveolus into the capillary, while carbon dioxide moves in the opposite direction, hence the term gas exchange. Gases are exchanged between the alveolar air and the blood by diffusion, the movement of molecules from an area of higher concentration to an area of lower concentration, where concentration refers to how much of one substance is present in a mixture of substances. The rate of diffusion is influenced by a variety of factors, including atmospheric pressure and the magnitude of the concentration gradient of the diffusing substance. In this lesson, we will discuss how atmospheric pressure and concentration gradients of oxygen and carbon dioxide influence diffusion and thus gas exchange. If you've ever been skiing or mountain climbing, you have probably experienced shortness of breath. You may have said or heard someone else say that the air is thin at high altitudes. Well, what does it mean to say the air is thin? A common misconception is that less oxygen is available at high elevations. As it turns out, however, the concentration of oxygen remains pretty much the same, regardless of the elevation. The concentration of oxygen is about 21% at sea level and on top of Mount Everest. Therefore, shortness of breath at high elevations is not due to less oxygen. That being the case, what causes shortness of breath at high elevations? To answer this question, we have to consider the effect of pressure on diffusion. Atmospheric pressure decreases as less air surrounds us at higher elevations, and pressure is needed to push oxygen into the blood. Let's look at this phenomenon in more detail. A central tenet here is Dalton's law, which states that the total pressure of a mixture of gases is due to the combined influence of the individual gases comprising the mixture. The pressure contributed by a single gas in a mixture is called the partial pressure of that gas. The equation for partial pressure is partial pressure of the gas equals the total pressure multiplied by the concentration of the gas, where a piece of gas equals the partial pressure of the individual gas, T sub P equals the total pressure, and then gas with the brackets around it refers to the concentration of the individual gas. At sea level, atmospheric pressure is 760 millimeters of mercury. Therefore, the partial pressure of oxygen would be 160 millimeters of mercury, or 760 millimeters of mercury times 0.21. The base camp for Mount Everest is about 5,000 meters above sea level, and the atmospheric pressure there is only about 400 millimeters of mercury. As the concentration of oxygen is still 21%, the partial pressure of oxygen is only 84 millimeters of mercury, or 400 millimeters of mercury times, again, 0.21. So you see at base camp, only 84 millimeters of mercury pressure pushes the oxygen into our blood, compared with 160 millimeters of mercury at sea level. Now that we've discussed how concentration and pressure affect diffusion, let's consider what happens to the concentration of oxygen in our lungs. Well, by the time the inspired air reaches the alveoli where gas exchange occurs, the concentration drops from about 21% to about 13%. At sea level, this reduces the partial pressure of oxygen from 160 millimeters of mercury to about 100 millimeters of mercury, as 13% of 760 is about 100 millimeters of mercury. What is responsible for this drop in partial pressure? Well, the addition of water vapor and carbon dioxide to the inspired air decreases the percent composition of oxygen. As you can see on the screen, the partial pressure of carbon dioxide in the alveolar air is about 40 millimeters of mercury. As we have stated, gas exchange occurs across a respiratory membrane. The respiratory membrane separates the alveolar air on one side from the blood on the other. Let's take a look at Henry's law. Henry's law tells us that pressure gradients affect the movement of gas into and out of a solution in a liquid. For example, carbon dioxide is added to soda pop under high pressure. As long as the can is closed, the carbon dioxide stays in the pop as the pressure in the pop is equal to the pressure in the can. Now when the can is open, the pressure in the can decreases, and carbon dioxide leaves the pop and enters the air. Well, the same thing happens in the lungs as the gases move in and out of the blood from a high to a low partial pressure. Now, blood entering the lungs is what we call oxygen poor, as it lost oxygen while flowing through the metabolizing tissues. Since the partial pressure of oxygen is lower in the blood entering the lungs than it is in the alveolar gas, oxygen diffuses into the blood. Carbon dioxide diffuses in the opposite direction. Since the partial pressure is greater in the blood entering the lungs than it is in the alveolar air. Again, the gases move from a high to a low partial pressure. It's important to note that for each gas, the partial pressures equilibrate or balance out across the respiratory membrane, and they do so as the blood flows through the lungs. Since the partial pressure of oxygen in the alveolar air is 100 millimeters of mercury, so also is the partial pressure of oxygen in the blood as it leaves the lungs. Remember, equilibrium is achieved. Likewise, carbon dioxide equilibrates across the respiratory membrane. So the partial pressure of carbon dioxide in the blood leaving the lungs is only 40 millimeters of mercury. Thus, the blood leaving the lungs is oxygen-rich and carbon dioxide poor. In summary, oxygen and carbon dioxide diffuse across a respiratory membrane. The rate of diffusion is determined by a variety of factors, including the concentration gradient of the gases and the partial pressure of the gases. Dalton's law can be used to determine the partial pressure of a gas in a mixture. Since inspired air is 21% oxygen and atmospheric pressure is 760 millimeters of mercury, that is at sea level, the partial pressure of oxygen is 0.21 times 760 millimeters of mercury, and that's 160 millimeters of mercury. As air moves into the alveoli, water vapor and carbon dioxide are added, and that reduces the partial pressure of oxygen to about 100 millimeters mercury in the alveolar gas. Henry's law is applied to gas exchange as the partial pressures for oxygen and carbon dioxide equilibrate across the respiratory membrane. And they do so such that PO2 is 100 millimeters of mercury and PCO2 is 40 millimeters of mercury in the blood after it flows through the lungs. Thus, blood leaving the lungs is termed oxygen-rich and carbon dioxide poor.